Let's understand this starter problem in problem set 3, applications of Newton's third law. We're going to do this together, and then the rest are for you to solve independently. For each of these scenarios, I want you to draw a physical diagram of the situation and then separate well-labeled force diagrams of the person. There's actually a mistake on here. Label any force pairs according to Newton's third law that occur on your diagrams. So we're going to imagine a person who's jumping vertically upward, but they're standing on a bathroom scale. Their legs are flexed and pushing on the scale, so their body's being accelerated upward, but they have not yet left the scale. Let's take a look at what this should look like. So first of all, person, scale, right? Knees flexed. Sorry for my artist's rendering there, that doesn't allow for that, but they are in the process of accelerating themselves upwards, still in contact with the scale. So here's my person, here's my bathroom scale. Start with the forces acting on the person. I know the person is being accelerated upwards, so I need to get to net force is up. The scale, on the other hand, is not being accelerated anywhere. And to be clear, I know those two things about net force based on what I know and can infer about the motion of the two objects I'm diagramming. Forces acting on the person include your typical and obvious gravitation, and something that's pushing the person up. So yes, their legs are pushing them up. That's part of the person. But that's them pushing down on the scale. The thing that's actually pushing them up is a normal force or an applied force. That detail's not important. By the scale, that detail's important. The scale is the thing pushing the person up. And it needs to be a larger upwards force than we have a downwards force of gravity. That's what I've shown in this picture. Now let's look at the scale. Yes, the scale has its own weight. That's thing one, Fg. Thing two, the person is pushing on the scale. Newton's third law suggests that this force needs a partner force going in the other direction. And the ground is supporting the scale. So let's start with that. Ground, I don't want to get ground and gravity confused, so let's call it floor. The scale itself has a weight. And then I talked about that this normal force needs to have a partner. So Fn by person on scale. Newton's third law suggests that those two forces highlighted in yellow are the same interaction, but viewed from two different objects' points of view. That's a Newton's third law force pair. Label any, oh, wrong color. My bad. Label any force pairs. So they're highlighted in yellow. Okay. Newton's third law also tells me that those forces are going to be equal in size, but opposite in direction. So I've attempted to show that here with the length of those lines on this diagram. I have also attempted to honor that the net force on the scale is 0. So show a situation where the forces on the scale balance out, and the net force on the person is upwards. So I need a longer up line than down line. So feel pretty satisfied with that. Let's move on to just after the person leaves contact with the scale. Person, scale. I would recommend, let's compare this to the previous situation. The person still has the same weight, Fg by Earth on person. And what else is the same here? Well, the person's no longer touching the scale, so the scale-person interaction, gone. Is the floor still supporting the scale, Fn by floor on scale? Yes. May or may not be the same size, but yes, it needs to exist. And FG by Earth on scale. So that's not going to be changed, right? And the person's weight. Wow. I can't identify any other forces that are happening to the scale. So it's just the weight of the scale, which means that after the person leaves contact with the scale, that normal force by the floor on the scale, that returns back to a smaller value. Net force is 0 on the scale. The person, on the other hand, absent the scale pushing the person up to accelerate them upwards, all I've got is a downwards force. This person's moving up while slowing down, right? The moment they lose contact with the scale, net force is down. We actually saw this previously when we studied free fall. We just didn't have a good way to explain it yet. This is what it looks like after the person leaves the scale. You'll notice that the Newton's third law force pair, that normal force that shows up in the first two pictures, highlighted in yellow, it's gone. There is no more Newton's third law interaction between the bathroom scale and the person jumping. Let's go to scenario C. Person, scale, person is coming down and accelerating down, bathroom scales beneath them, right? All right, person's coming down, slowing down, coming down, speeding up. Oh, wait, hang on. They're in the air. That's exactly this situation. I'm going to save myself a little time. Bear with me, I didn't plan that ahead terribly well. That's exactly the same situation as when they were first leaving the scale, right? The Earth is accelerating the person downwards, except the difference is they're coming downwards now, so it's causing them to speed up. Bathroom scale? Hey, wait, person's still not touching the scale. They can't be interacting with it. So I get to duplicate another picture. Boom. All righty, last part. The person has just hit the scale. Their knees are flexed again. They're slowing down. So they were moving down, but now the acceleration is upwards. I know that seems a little weird. Why is the acceleration upwards? They're moving down and slowing down. That means you need to have an acceleration upwards and a net force upwards. The scale still experiences 0 net force. It's not accelerating anywhere. All right, person's in contact with the scale. They're slowing down. Is it possible that this is the situation we're looking at again? Let's see if this makes sense. So first of all, person's in contact with the scale. They need to be slowing down. If this diagram shows an object that's moving down while slowing down, I would need a net force upwards. That's totally this picture. How about for the bathroom scale? Same situation again. Okay, so to be clear on what I'm saying here is the person's knees or legs are flexed, and the scenario where the person is coming back down and legs are flexed, but they're slowing down, those are exactly the same force diagrams. Accelerating upwards or slowing down when they come up, same situation. Newton's third law once again says that because the bathroom scale and the person are interacting, that there is a Newton's third law force pair highlighted in yellow between the two objects. This example was built to make you think about a scenario at multiple moments in time and to think about how Newton's third law dictates that some forces are identical when they act on two different objects because it's actually the same force viewed from two different angles. That's the whole problem here today. Best of luck as you continue the problems.